Okay, let's talk a little bit more about these distance time graphs. I think my thing got turned a little bit. There we go. Okay, so for this one here, question number 3 says, which line shows an object that's increasing in speed? So if we're increasing speed, we're looking for an acceleration, right? Well, if you think back to yesterday, when we talked about acceleration, what does that graph, that line, look like on a distance time graph if something's accelerating? So let's look at these two right here. We've got object A is this nice, pretty straight line right here. It's at that nice angle. It's perfectly straight all the way through. Is that something that's changing speed, or is that at a constant speed? This one right here. If you said that's at a constant speed, you're exactly right. So if you see a nice straight line on a graph that's at that nice diagonal, you got a constant speed. Well, if it's a constant speed, it's not increasing in speed, is it? Nope. It's not increasing. It's the same. It's a constant speed, okay? So if we could process of elimination, if it's not this line, it's got to be the other one, which that wouldn't be wrong, but we're going to talk about it, okay? Let's look at this line right here. So I'm going to make this one blue so that I know that you can see it really, really well. So let me go, we've got a nice little whoop going up right there, okay? So let's talk about this line. We're looking for an increase in speed. So we're going to look at two different places on this line. We're going to look from here to here, and then we're going to look up here. But if you look from just this part right here, that line is almost horizontal. And if it's horizontal, that means it's stopped, right? Well, it's not quite stopped. It's got a little bit of an angle on it. So that means they're going really, really slow, okay? So right down here, we're going slow, okay? Well, let's look further up our line, right up here towards the top. This line right here, now that one is almost straight up and down. Well, if that line's almost straight up and down, that means that they're going super fast, okay? So I'm going to put fast right there. If we're going from slow to fast, that means our speed is increasing, okay? So this little whoop right here, where we're going slow to fast, boom. We know that's the line that's showing an increase in speed because that's acceleration, okay? I do love these distance time graphs. Let's see, what do we have next? All right, question number 4 says, how far did object A travel? Okay, well, object A is this red line right here. So that's object A. We need to know how far it traveled, okay? So how could we figure this out? We want to know its distance. If we just want to know distance, would we look down here at the bottom? Well, it says time in seconds at the bottom. That's not the question, right? The question is distance. How far did it travel? Well, here's our distance right here. In order to figure out how far it traveled, we could just go to the end of the line right here and bring it straight across, and we would see that we traveled 100 meters. See how this line starts from right here? If we brought it over, boom, 100 meters. That's how you tell the distance. So we've got 75 meters, 20 meters. There's 100 meters. And 100 meters is our answer because we just went to the end and we came over to the side. Pretty neat, right? Okay, well, let's look at the next question. Question number 5. Question number 5 says, what was the speed of object A? Well, we can figure that speed out just like we did a couple slides ago, okay? Because we've been figuring out speed for days. Speed equals distance divided by time, okay? Speed equals distance divided by time. For this one, we'll go right back here at the end. we already figured out if we go over to the side, our distance is 100 meters. Let's go down, 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 down. And we've got 20 seconds, okay? So we went 100 meters in 20 seconds. Well, now we have our distance and we have our time, so we can figure this out because speed equals distance divided by time. So let's put a spot for our distance. Here's a spot for our time. And that is where we can put our answer. So our distance, right here, we followed it across, is 100 m for meter. Our time, we follow this line straight down, is 20 s for seconds, okay? Let's do some math on that. And like I said, make sure you use that calculator. 100 divided by 20 is 5. If you can do that in your head, that's perfectly fine. If you don't want to, that's fine too. So 100 divided by 20 is 5. We can't have willy-nilly numbers sitting around here. We're in science class, not math. So we got to bring our units down. There's an M for meter, an S for speed, for seconds. So 5 meters per second is this object's speed. So here we've got 200 meters per second. There's 5 meters per second. That's our answer. So this is just like the formulas that we've been talking about, or the formula we've been talking about, speed equals distance divided by time. Only instead of getting the numbers for distance and time from the word problem, we're getting it off of this graph. Kind of cool, right? It's a little bit more fun. Uh-oh. I don't know what I just did right there. Okay. There's question number 5. Let's look at number 6. We got a different graph to look at here. Okay. The question for number 6 says, which part of the graph shows that the object is returning to the start? Which part of this graph shows the object going back home? Well, let's see. A is just a line straight across, straight horizontal. Well, we've already talked about that. If we've got a horizontal line, that means that it's at rest, right? So it can't be A, because at A, the object is at rest. Well, let's look at B. So B is this line right here, okay? We've got a nice diagonal line. We're moving at a constant speed. Super cool. But if you look at your distance, it's moving away from the starting point because it's going up. If it's going up, it means it's going away from the starting point. We want something that's coming back to the starting point. So we want somebody that's coming home, right? Well, let's look at C. We've got C starts up here and goes down. Well, that's exactly what we are looking for because we're looking for something that's going back home. That's going back to the starting point. So here we start and we're going down. That's exactly what we're looking for. If you've got a line on your graph that's angled downward like this one, that means you're going back home. So C is the right answer for this question right here. Let's see what we've got next. Okay. All right, question number 7. This is the same graph we were just looking at. It says, which parts of the graph show that the object is traveling at a constant speed? So which parts on this graph right here is the object traveling at a constant speed? Well, what are we looking for to find something that's moving at a constant speed? We're looking at a nice smooth diagonal line, remember? And that diagonal line can go in either direction. Someone can move at a constant speed moving away from home, or they can move at a constant speed if they're going back home. Either way, they can move at a constant speed. So let's look at our graph right here. This section right here, A, that's a horizontal line. That's not at a constant speed. They're not at any speed at all. They're just sitting still. If we've got a horizontal line like this right here, we're just sitting still. So I'm going to cross that one out. That's not it, right? Well, B is one of those nice, pretty diagonal lines. It's not angled. It doesn't have any whoops in it. It's not horizontal. It's a nice diagonal line. they are moving at a constant speed right there at B. So I'm going to circle that one because that's a constant speed. Let's look at C. Well, that's still a nice diagonal line. It's just facing a different direction because they're going home. Well, it's still a diagonal line, so they can still be going home at a constant speed. So both of these lines right here, this car is moving at a constant speed. So our answer is going to be B and C. So there it is right there. Pretty cool, huh? Man, I like these distance time graphs. You can get so much information off of them. Let's see, what do we have next? There we go. Let's clear that off of there. Okay, we got a bicycle, okay? Our question is, how long was the cyclist stationary for? And remember, this stationary word just sounds fancy for at rest or standing still or not moving. Any of those, stationary, okay? So we want to know how long he was stationary for. What type of line are we looking for if somebody is stationary or at rest? If you said a horizontal line, you are exactly right. So let's look for the horizontal line right here. This isn't it. That's a diagonal line. This one over here is not it. That's a diagonal line too. So we want this one right here in the middle. This cyclist is taking a rest. He's hanging out. We know he's at rest because we have a horizontal line. We need to figure out how long he was stationary for. So it might be hard for y'all to see, but I'm going to tell you, so that's okay. He stopped at 60 seconds, okay? And he stayed at rest from 60 seconds all the way to 140 seconds. So 60 minus 140, or probably have to be the other way around, but you get where I'm going with this, right? So how many numbers are between 60 and 140? That's the amount of time he was at rest. So if we counted right here, you could just count. It looks like there's 10 seconds in between each one of these lines right here. We could say 10, 20, 30, 40, 50, 60, 70, 80 seconds, or we could do the math on it. 140 minus 60 is 80. So the time in between here and here, 80 seconds, okay? So that's our first option right there, 80 seconds. That's how we would figure that out. So you just gotta figure out what time he stopped, what time he started moving again, and find the difference between those two numbers, okay? Let's see, what do we have next? Might have to go to the next one too. Oh, okay. Cool. We just have to click on stuff. Alright, so we're going to match the deal down here, the scenario, with the graph. So let's take a look. This one says a car travels at 60 kilometers per hour for 2 hours on the motorway. It stops at a service station for 2 hours, then travels in heavy traffic for 15 kilometers per hour for 30 kilometers. Okay, so we're moving away from home the whole time. We know that just by reading it, so this would make sense. Okay, so a car travels at 60 kilometers per hour for 2 hours. Let's look at right here. This is hours, so there's 0, there's 1, there's 2, okay? So that's the first one, so that checks out. He said he travels at 60 kilometers per hour for 2 hours. If we wanted to do the math right here, we could figure out how fast, exactly how fast this car is going by doing distance divided by time. Okay, so if we divided our distance into time, we'd get 60 kilometers per hour. Then let's see, it says it stops at the service station for 2 hours. Well, here we've got 2 hours that the car stopped for right there. So they're at rest. We know they're at rest because we've got that horizontal line, okay? And then it travels in heavy traffic for 15 kilometers per hour for 30 kilometers. So let's look at the difference right here. We can tell it looks like he's going slower than he did here, right? So that would make sense that he was in traffic and had to move a little bit slower. We've got 20 to 50. Well, 120 minus 150 is 30 kilometers, so that makes sense. This graph exactly matches this scenario right here, okay? Well, let's look at the next one. This is about a toddler. This says a toddler rides his bike up the pavement for 10 minutes. He then turns around and rides back 2 meters from home. He hits a bump and falls off of his bike. Well, that's kind of sad, poor little thing. All right, so a toddler rides his bike up the pavement for 10 meters. So he starts here, he's riding his bike. We've got our numbers right here. There's 2, 4, 6, 8, 10 meters. That's exactly what it says right here, 10 meters. He then turns back around and rides back. So he hung out for just what? 2 seconds right there. That's okay, that's 4, 6, 8. So he hung out for 2 seconds before he spun around, okay? And then he turned around and headed back. Well, we know this graph is heading back home because it's at that downward angle, right? So there he's heading back home, but he fell off right before he got there. So this graph doesn't go all the way back home because he fell off his bike right there. Makes sense, right? So we can see this whole scenario right here in this graph. I think it's kind of cool. All right, let's look at the last one. The last one says, a coach leaves the station at 10 a.m. and reaches a town at 11:30 a.m. where it stops for half an hour. Then it carries on for 30 minutes, reaching the next station 40 kilometers later. So a coach is just a fancy word for a bus, okay? So here we've got a bus. It leaves the house at 10 a.m., leaves the station at 10 a.m., so there we go. We got hours right here, okay? Leaves the station at 10 a.m. and gets to another town at 11:30. So 10 a.m., 11:30, we do some math on that. That's an hour and a half, okay? So here, we've got an hour and a half. So there's 30 minutes. There's another 30, another 30, okay? So that's 1 hour, 30 minutes. That's an hour and a half, right? So there's travel at a steady speed, paused for 30 minutes, for a half an hour. So there's their pause, where it's a horizontal line. And then it continues on for 30 minutes. There we go. Continues on for 30 minutes, and then found another station. It's kind of neat, right? How these scenarios can match up so perfectly with the graph up there. All right, let's see what we've got next. Okay, let's look right here. What does this distance time graph show at each of these points? So A, this is where we start. Well, we'll do that one another day. That's okay. Y'all, go ahead and answer the questions. Remember, we just talked about everything that's going to be in the questions below. If you forget something and you think, man, I just don't remember, come back up and watch this video again because the answers are all going to be in here. Y'all are amazing. We'll see you later.